So let's start off with talking about ionization energy. Now this is a good place to start because we are very familiar with ionization energy. We've been talking about it in a lot of different forms for quite a while. It's that minimum energy required to remove an electron from an atom. And specifically, when we talk about ionization energy, it's assumed that what we mean is actually the first ionization energy. So you can imagine we could talk about any of the different electrons, or we could talk about taking out an electron and now taking out a second electron. Whenever you hear the term ionization energy, make sure you keep in mind that unless we say otherwise, we're talking about that first ionization energy. And we know what that's equal to. This is something we've been over and over. Ionization energy is simply equal to the negative of the binding energy. So negative E, which is sub NL, because it's a function of N and L in terms of quantum numbers. So let's think about kind of differentiating, however, between first ionization energy, or just ionization energy, and other types such as second or third ionization energy. And let's take boron as an example here. So if we want to think about what the first ionization energy is of boron, what you want to do is write out the electron configuration, because then you can think about where it is that the electron's coming out of. The electron's going to come out of that highest occupied atomic orbital, that one that's the highest in energy, because that's going to be the least amount of energy it needs to eject something. So what we'll end up with is boron plus 1s2, 2s2. And what we say is the delta energy, or the change in energy, is the same thing as saying the energy of the products minus the energy of our reactant here. And we just call that the ionization energy. That's how much energy we have to put into the system to eject an electron. And again, this is just the negative of the binding energy when we're talking about the 2p orbital. So this is first ionization energy. Let's think about second ionization energy. So second ionization energy simply means you've already taken one electron out. Now how much energy does it take for you to take a second electron out? So in the case of boron here, what we're starting with is the ion, boron 1s2, 2s2. And now we're going to pull one more electron out. The highest occupied orbital is now the 2s orbital. So we're going to end up with boron 2 plus 1s2, 2s1 plus the electron coming out of there. And what we say when we talk about the delta energy is that this is going to be equal to IE2, or the second ionization energy, or we could say the negative of the binding energy of a 2s electron in B+. So it's important to note that it's not in B. Now we're talking about B+, because we've already taken an electron out here. So similarly, if we start talking about our third ionization energy, this is going to be going from B plus 2 to 1s2, 2s1. Now we're going to pull that second electron out of the 2s. So we end up with boron plus 3, and then the configuration is just 1s2 plus our extra electron here. So what we call this is the third ionization energy, or the negative of the binding energy, again of the 2s orbital, but now it's in boron plus 2 that we're starting with.